So once the Renaissance occurred, where people were going back to original sources and thinking for themselves and started going about things in a systematic way, in a scientific way, you started to have a trend towards disputing with long-held views, even powerful views. People were thinking for themselves, and they were measuring and observing from themselves, and some of the theories that they had been taught did not work. And so during this 14, 15, 1600s period, astronomy was flourishing. Okay? Astronomy was one of the subjects taught during the medieval universities. Every student that went to college studied astronomy, but their study of astronomy wasn't looking at the stars necessarily and measuring things and trying to come up with new ideas or explanations. They were more studying things that had already been written. So they would look at Aristotle, they would look at Ptolemy, they would look at some of these old Greeks and who wrote books, and read those books, and that was their study of astronomy. Some people, though, would look for themselves, and they would measure for themselves, and some of these theories, they, in their opinion, didn't hold water. So we're going to look at a few of these. We're going to look at Copernicus, the Polish, I think he's a monk. We're going to look at Tycho Brahe, which is a nobleman from Denmark. We're going to look at Johannes Kepler, who is an astrologer from Czechoslovakia. We're going to then look at Galileo Galilei, who was just a gentleman from Italy, and then Isaac Newton, who on his summer vacation from college invented calculus. So some of these are the smartest people that's ever lived, and what they did with what they saw is why they're well known, and they're well known for a reason. Next, we come to Nicholas Copernicus. Nicholas Copernicus was a clergyman. Of course, all of that time was all in the Catholic Church, and but he was a scientist on the side. Very, very smart fellow. And from what he observed, he did not like Ptolemaic theory. Even with the idea of the epicycles and all that was crowded in to try to make things make sense, it didn't perfectly match what he was observing. So when your theory doesn't match your observation, there's something wrong with your theory. That is a scientific idea. An idea is that the data is always right. What you measure is right. Your theory can change based upon what you see. So if you can measure something more specifically and your theory doesn't go along with it, if it's not broad enough to encompass the observations or the measurements that you're making, then there's something wrong with your theory. And he saw lots and lots of holes in Ptolemy's ideas. Okay, though that he knew that Ptolemy was smart, it wasn't about being smart, it was about being right or wrong. So he saw that Earth was a planet just like the other planets that they knew about at the time, and that Earth was not stationary, but actually spinning on its axis. If the stars are not moving and Earth is moving, it'll look like the stars are moving. Okay? Now, the problem was that people that expressed this idea, people would laugh at them and say, if the Earth is going around, why doesn't the houses fall over? Why doesn't the apples fall off the trees? If you're going around, whirring around in a circle over your head, after the other, the whole Earth should shake apart. And Copernicus recounted, well, if the Earth is the small and the stars are bigger, if the stars are moving, why doesn't the stars fall apart? Because that would even be harder to move all that huge amounts of stuff as fast as it happens. Okay, so he was doing arguments, he was doing counter arguments, and he was simply just looking and saying it doesn't match, it can't be right. The big problem at the time was that the Roman Catholic Church had the idea that the earth was the center of the universe. Okay, when Christ came to earth, that made the earth the important place in the universe. Okay, and specifically the center of the earth was Jerusalem, and the Earth was the center of the solar system, and the solar system was the center of the universe. And that lined up with Ptolemy. Now, Ptolemy didn't have the same views at all, but the church loved this and did not want to go away from it. So Copernicus wrote a book called The Revolutions of the Heavens, and he dedicated it to the Pope, and he published it as he was dying. They published it the day that he dropped dead. Okay, he was smart because he knows that the Inquisition gets a hold of you, they'll burn you alive. And there were others that held to the Copernican view that did pay for it by burning at the stake. It was a dangerous time to have your own ideas. Okay, but Copernicus was the first to write about this. He wrote about it, and he gave math, and he gave reasons, one reason after another, and we'll look at a couple of these. In Copernicus's book, he gives lots and lots of reasons why that he believes that the Earth is a planet, okay? And that the Ptolemaic, or the theory that Ptolemy had put forth, that was all in everybody's books, everybody in school studied the same guy. He was the guy, he was right. The problem that he had with it is that it didn't work. Like when you actually looked at the planets, because Ptolemy wasn't really a scientist, he was a philosopher. And he was making the universe work according to his idea of it, rather than change the idea based upon what he saw. That's the difference between philosophy and science. Philosophy is the love of wisdom, or the beauty of your thinking. Science is, who cares if you can think or not? You're simply making measurements and then trying to understand what's actually happening based upon those measurements. All right. So if you were to look at Venus, and Venus was going around in an epicycle circle above Earth, then you should see almost like a crescent moon shape on Venus. You're either going to have a new moon or you're going to have a crescent moon. You'll never have a full moon. Now, it's not a moon, it's Venus. You'd never see Venus as a circle, because the way a full moon would be is if it's on the other side of the Earth from you. But if it's all on the same side, you can't see a full shape. But if it's going around the sun and the Earth is also going around the sun, sometimes you'll see it as a crescent, sometimes you'll see it as a dark disk, and sometimes you'll see it as a complete bright disk. That makes sense. So he's using arguments, and this is just one of the arguments that he's using. This brings us to another really great in the history of astronomy and in the history of thinking, and this was Tycho Brahe. Tycho Brahe was a Danish nobleman, so he was rich. He was rich enough to have nothing to do all day. He was a gentleman. He had lots of money and lots of people serving him, and he was interested in astronomy. He also suffered greatly from insomnia. He could not sleep at night. He would lay down, and sleep would never come to him. So he worked all the time and kind of slept in little fits and starts, 5 minutes at a time. But because he stayed up all night, he was able to see the stars and the planets, and he was more interested in the planets because the planets moving around was different from the way that the constellations moved in the sky. And so he was willing to actually make some measurements. He would plot in his diary every night where Mars was, and is Jupiter in the sky or not? And if so, where was it? Exactly in the sky where it was. And he did this night after night and night after night for years. Now, he did not like Copernicus's idea that the Earth was the center of the solar system. Not for religious reasons, he didn't have a problem with that. He simply had this idea of parallax. Now, he's brilliant, and he was absolutely right, and I'll try to explain what parallax is. Let me just explain it this way. If you were to hold your finger out and close one eye and look at your finger, okay, then close that eye and open the other eye, your finger appears to move because your eyes are not coming from the same spot. One eye is to the left and one eye is to the right. So if you were to if you were to hold your finger really, really close to your face, close one eye and look at it through one eye, then close that eye and open the other eye, it appears to move a lot. If you were to move your finger out as far as your arm is and now do it, it doesn't appear to move as much. Okay, now this is called stellar parallax. All right, so imagine that if the Earth is moving, rotating, okay, now this is really what he was talking about. If the Earth is stationary, like Ptolemy said, and doesn't move, and only the stars and the planets move, okay, then no big deal. But if Copernicus is right, and the Earth is a planet, and it's rotating on its course, like it's rotating, first of all, why don't we feel it? Why doesn't it feel like that we're in a moving boat or a moving car? Why don't all of us get car sick because we're spinning and spinning and spinning at 1,000 miles an hour? Okay, so he thought the major problem of why the Earth did not spin was because if you were to look at a star and then 6 months later look at a star, the appearance of that star should have moved. Okay, now he's not looking at planets necessarily because the planets are moving too, but he's looking at these stars that don't move, and everywhere every night in the sky are at the same place. So it would be like if I'm on one side of the Earth, and then 6 months later, I should be on the other side of the Earth on the same night, same time of the night. If it's moving, if the Earth is moving on its axis, then I should look at that star, and it would be like looking at my finger. It should be in a different place in the sky. He didn't see it, okay? And because he didn't see it, he didn't agree with Copernicus. Now, that's a great reason not to agree with someone. Fantastic reason. Even though Copernicus gave other reasons why that the Earth was a planet, just like the other planets, Tycho Brahe was going strictly on data, okay? Now, if you looked at your finger real close to your face and then looked at your finger farther from your arm, you'll see that it doesn't move as far. The farther that point that you're looking at gets, the less difference they will be. So what Brahe, his problem was not that he wasn't smart and able to see that there should be a change, but he was underestimating how far the stars are. He thought the stars were just beyond Jupiter, that you have these planets, and then right past planets is a place of fixed stars that are not moving, okay, and that are all together like on a dome. And if they were just as far as Jupiter, you should be able to see parallax. You should be able to see that there's a different place in the sky. But because they didn't, he didn't agree, okay? But Tycho Brahe wasn't known for his brilliance as much as just he was able to make data. He wrote a book full of where Jupiter was, where Saturn is, where Mercury is, where Venus is, where Mars is, not Mercury, all on and on and on, night after night, that later Kepler uses. Now, when he loses his job in Denmark, he starts working for the Holy Roman Emperor. I believe his name is Francis the First or something, Francis, I think. In any case, when he gets to Prague, where the king lives, he works for him. And he gets an assistant named Johannes Kepler, okay? And Kepler will be the next person that we look at. So this brings us to Johannes Kepler. Kepler was Tycho Brahe's assistant once he got to Prague, and they were both in service of the Holy Roman Emperor. So this is one of the major kings in Europe during the time, most powerful men in the world. And so Kepler, it turns out, really wasn't his scientist. He was his astrologer. So astrologer was basically finding out like his fortune teller. But Kepler was probably one of the smartest people alive. He just needed a job. So he had a job, and after Tycho Brahe died, Kepler inherited all of his notes. And he saw in his notes that for 10 years, every night, Tycho Brahe had plotted the course of every one of the planets. He knew where in the sky they were every night of the year for 10 years. That is an amazing amount of data. Now, everybody could have had that data. I could have had that data, and it wouldn't have done me a bit of good. It would have just been a list of locations. This planet was this many degrees up and this many degrees from the top of the sky, this many degrees from east-west. All it was meticulous plotting of points in the sky. Well, as Kepler looked at those notes, his brain was able to see more than most people. And he realized that it cast a problem on some of his assumptions, some of the things that he held to, and also that some of the problems that other people's ideas, previous ideas had. For instance, perfect circles just wasn't the way that the planets actually traveled in the sky. Also, the epicycles, no way, it just doesn't work. Where these planets would have had to been didn't match what was written in the book. So he was going straight from the data. That means that he was absolutely doing science. He wasn't trying to make up something. He was trying to describe something that he saw, that he could measure. And whatever that outcome was is what he did. And that's why he's one of the greats. Now, on the board behind me are his 3 laws. And he basically did this on his spare time. I don't know, he must have been a nerd. To look at this data from this old dusty book from this guy that he worked for and piece it together bit by bit by bit to understand what was really happening with the planets. So let's just take one planet, Mars, okay? Mars did not travel in a circle. It couldn't have traveled in a circle and been in the part of the sky that Brahe said it was, okay? So he tweaked it a little bit, and eventually he came up to the idea that it must be an ellipse. And now an ellipse is kind of like an oval, but there's a math formula behind it, okay? Whereas a circle, the radius from the center to the edge of the circle is exactly the same everywhere. That's a perfect shape. An ellipse has 2 focal points. And essentially, if you were to put a thumbtack at the 2 points, okay? I show you there's the other focal. It's kind of small. So there's the focus. There's nothing there. And then the sun is located in the other focus. All right? If you were to put a thumbtack in each of those 2 points and then have a string that was long enough to go to the outside, everywhere you went, you could trace that ellipse because it's the sum of both of the radiuses, the radius from here and the radius from here, and it basically traces that path. So he saw that it was working in an ellipse, which is a mathematical formula that he could understand, and he wrote it out. Also from the data, I think even a smarter, harder to understand thing was that in the same amount of time, the speed of the planet changes, okay? So when it's in one part of the sky, it's going very slowly. When it's towards the sun, it goes fast, all right? So it's almost like a slingshot. It's going fast and it slows down, and then fast and it slows down again. So the way he mathematically wrote it was the area of this imaginary line between the orbit and the sun that traced out, that area is mapped out in the same amount of time that this area is mapped out. But since this is farther away, these 2 areas are identical. So in the same amount of time, the area that's mapped out by that moving planet is exactly the same at all times. So if you were to take a month, the same amount of area is mapped out in a month, whether it's at the closer to the sun or farther from the sun. So smart, okay, so smart. Guy didn't even have an iPhone to work on. Everything was done with paper, and he had to dip the ink in the pen in the ink. The last one is, I think, the easier of the idea, and that is that the period that's the time it takes to go around the sun, is proportional to how far away from the sun. So Mercury, which is closer, will have a very fast period, so its year won't take very long. Then the Earth has 365 days. That's a year to Earth. The year to Jupiter is going to be more than a year for the Earth. It would take more than a year. Pluto could be into the very many years, okay, to go all the way around the sun. So the farther it is, the slower it's going to appear to take to get all the way around. If you were to imagine Mercury and the Earth going at the same speed, okay, to where the Earth was going in 1 year all the way around and Mercury had the same year, then Mercury would be going really slow and Earth would be going really fast, because the farther you out towards the end of the circle, the faster you have to go to keep up with it, okay? So he saw too that these distances, okay, these distances are distances from the planet to the sun. And later that's going to be called an astronomical unit. We name an astronomical unit for Earth, okay? We get to pick because we're Earthlings. So 1 astronomical unit, or 1 AU, is the distance from the sun to the Earth, and that is considered just a distance as you can measure large things in. Here's a picture of that second law of Kepler. So strangely enough, the Earth is closer to the sun in the winter than it is in the summer. You would think that since we're in the northern hemisphere, summer is warmer than winter, but we're actually closer to the sun during our winter. The southern hemisphere is pointed towards the sun. They get most of the light. We don't. But so it's moving faster. It's moving in space at a quicker speed during the time that it's closer to the sun. And then as it goes away from the sun, it slows down. But the blue shaded, or the dark blue shaded here, is indicating that the area of the big fat short triangle is equal to the area of the little long skinny triangle, so that in the same amount of time, even though that the planet slows down and speeds up, it's moving a certain amount of area equal to each other. And there is your uniformity, that it's always making an area the same in the same amount of time. We now come to my hero Galilei, and he has the first and last name. His name was like John. So Galileo, and son of Galileo. So Galileo Galilei is his name. And he was an Italian. He lived near Venice, and Venice was a port city, and rich. Now at that time there was no king of Italy. Every little city was their own kingdom, and so you had dukes of all of these different places. Now he was of course very, very smart, and he loved tinkering with things. He is the guy who came up with the idea that of inertia, which becomes the first law of Newton, which objects in motion stay in motion, objects at rest stay in rest unless acted upon by another force. That's his idea. Newton just completely lifted it, and everybody knew that it was Galileo's, but Newton put it into his laws of this is the way the universe works. So Galileo studied all kinds of different things, and in his study wrote. One of the things he's known for in terms of astronomy is that he invented the telescope, which is so not true. He did not invent the telescope. Let me tell you the story. So evidently, he read a report or heard a rumor, okay, that a guy in the northwest, Holland area, Belgium area, had invented a telescope, and that he used convex lenses, 2 convex lenses in a tube, a leather tube, and that you could see far, far away, okay? So that's all he needed. He said, okay, somebody has invented something that can see far away with 2 convex lenses. So he just said, I'm going to make one. He had never seen one. No one had ever seen one. He only heard a rumor that it had existed somewhere, okay? So Venice was a place where glass was made all the time. It was one of the best centers for glass in the whole world. And so he went and ordered 2 lenses. Now, he told the glassmakers exactly what to do. And remember, convex are bumped out on both sides, just like eyeglasses would be. Okay? And he had a small one and a big one. And he put it in a leather tube, and he played with it so that you could move the tube, and invented within just a couple weeks, because he was afraid that somebody else was going to come with this telescope because he had an idea. If you are the Duke of Venice and you're so worried that someone's going to attack your city from the sea, okay, because that's what you would do, that you would come and bring in a navy and you would conquer the city. If you were worried about that, you would want to be able to see a ship coming far, far away as fast as you could. So Galileo got the town fathers up in one of the towers in Venice, and he said, if I could let you have 1 hour notice when a ship is coming over the horizon, would you pay me a lot of money? And they said, absolutely. If we could have 1 more hour of notice that a ship was coming, yes, we would pay you a lot of money. And so he pulls out his telescope and he said, look through this telescope. And as they looked, they could see a ship farther away than they could see with their eyes. Well, he's instantly rich. He now lives, basically doesn't work. He just has plenty of money in the bank, and he just goes and puts himself into his full-time research. Now, he has a problem, because the more he studies and the more that he reads, the more he realizes that the Earth is not the center of the solar system and that the Earth is not stationary. Everything is making him believe that Copernicus, that he read Copernicus's book, was right, and that there's the heavenly bodies that are moving includes the Earth that's moving as one of the planets. But it's a very dangerous time to have your own ideas about this. And he was in the middle of the head of Roman Catholicism, which was Italy. So he wrote some things and agreed with Copernicus. Okay, now Copernicus was, no one liked him in the upper-ups. The people did not like the idea that the Earth was not stationary in the center of the universe. And so they brought Galileo to the Inquisition. And by this time he was an old man. He was well known. They were going to burn all of his books. They were going to burn him at the stake. And they basically said, take it back. You don't believe that the Earth is not stationary, and you don't believe that the Earth is the center of the solar system. And he basically, to save his skin, said, oh, I'm sorry, I was stupid. The Earth is not moving. Of course it's not moving. I don't know what I was thinking. I must have been asleep. And the Earth is not the center of the solar system. So he recanted and lived in house arrest in his villa for the rest of his life. A lot of people that did say Copernicus was right paid for it with their life. Copernicus, remember, wrote his book on his deathbed, but Galileo didn't want to put up with it, and so he recanted. But of course, everyone realized that what he had written was what he had written, and that he believed just because he signed the paper that the Inquisition given him didn't mean anything, and most people would have recognized that. So this is Galileo's telescope, and it's still in the museum near Venice. And in his notebook, he was the first to look at the moons of Jupiter. He was able to see moons through his telescope. He was also able to do the first drawings of the moon and all of the pock marks on the moon. From the impact craters that are on the moon, and he was the first to see these planets that no one else had seen. Now, people with their just naked eye could see Jupiter, but he could not see the planets in front of Jupiter. And he also said these planets are not going around the Earth. These planets are going around the planet. So these are moons of Jupiter going around Jupiter, just like our moon goes around Earth. So, and it was data that anybody that looked through the telescope could see. So he said it, he wrote it, he published it. He didn't say again what he was in trouble for, but this is enough to get you in the history books. But Galileo has done 10 million things to get you in the history books. It was his telescope that made him think that Copernicus was right. So if you look at Venus, you're going to see that Venus sometimes is a full disk, sometimes is a dark disk, sometimes is a crescent disk. And just like the slide I showed you before, if Venus is going around in a circle away from you, then you should only see crescents. And it was this that convinced Galileo that Copernicus was right, even though that he recanted and signed the Inquisition later. This was what he believed. Last on our list is Isaac Newton. And Isaac Newton was at college, and they closed the college because the plague broke out. So they sent everyone home. I think he was 21, maybe 20, and he was home. And so he just came from a small place in Lincolnshire up in the middle of England, and beside his house is an apple orchard, saying that you can still go to his house today. Now, whether or not an apple fell on his head, no one knows. But the story goes that he was sitting there with nothing to do. He was home from school, and he was sitting under an apple tree, and he was looking up through the branches of another apple tree and looking at the moon. The moon was in the sky during the daytime, like you've seen it a million times, and he was looking at the moon, and while he was looking at the moon, an apple from that tree fell to the ground. And the apple caught his attention, and the question in his mind instantly was, why did the apple fall to the ground, but the moon doesn't fall to the ground? Why doesn't the moon act like the apple? Okay, so that was the first question that eventually led him on his work to think about what masses do when they're close to each other. Masses exert a force on each other that is called gravity. And so Isaac Newton was the first not to think about gravity or understand that it happens, that everybody knows you fall down and go boom. But Isaac was the first to put it in math terms and to write it. Now, in order to describe what he was doing, he had to come up with a new mathematics called calculus. He invented calculus in order to describe what he saw in his studies. We're going to see that calculus is ascribed to two different people at the same time. A fella in Germany was coming up with it at the very same time that Isaac came up with it. Isaac had it in a drawer for 25 or 30 years. He just used it because that was helping him to describe how gravity worked. And then he heard a rumor that this other guy was going to publish a book, and he published it first. Okay, so typical ego. He was smart as he could be, but he also knew his place in history, and even during his lifetime, he was revered. Isaac Newton in England was as famous as the king. Okay, so because of what he did. He also opened up the possibility that you could study the universe and know its laws, that you could follow God's mind, that God was okay with it. He was the one who invented it, but men could understand it. And that was a big rubber band that sent science forward. As people said, well, we can study anything. If we could study gravity, then we must be able to study anything. And people immediately started studying every imaginable thing in the universe that they could see, not just astronomy, but everything. And they were writing books, and societies were coming together where they would review each other's work and listen to each other's work and ask questions and probe each other. And so the scientific community really was birthed during this time. The other thing that his theory did was other things that were true, including Kepler's laws. Isaac Newton's work on gravity backed it up. So, for instance, if you have a gravitational force which pulls that planet in towards the sun, okay, but yet the planet is moving and has momentum and is going in a certain direction and it wants to go in a straight line, then the gravitational pull will force it off of that straight line and into a curved path. Well, this gravity theory, if you look at it based upon how does Kepler's law work, it makes Kepler's work even stronger. Okay, so what a good theory does is it's not just a theory that works for what you're talking about, but everything that touches it will support it. Okay, so everything that is true, one theory on one subject can reinforce something on another subject. And eventually now, gravity is no longer called a theory, but it's accepted universally by everyone, and it's referred to now as a law.